Flipped classroom video for Maths AS Unit 1, revision of circle theorems with proofs. So we'll have a look at the Gcse circle theorems. The thing about this is that these are going to be assumed, most of them anyway, in contextual questions that involve circles. So it's a good idea to revise them and to make sure you remember them. So we've got the angle in a semicircle is 90 degrees. You may have been taught that the angle subtended from the diameter in a circle to the circumference is 90 degrees. There's different ways of saying it, but the main thing is that you know and remember the basic facts of it. If we take 2 points on the circumference and make angles at them from a particular arc, so the arc AB, in this case this is the one in the middle now, at the top, then the angles at the circumference are equal. If we have an arc and we do the angle to the centre and then an angle to anywhere on the circumference, then the angle at the centre will be double the one at the circumference. In a cyclic quadrilateral, so this is now the left hand side in the middle, a cyclic quadrilateral is just any four-sided shape where all the vertices are on a circle. Then we have that the opposite angles add up to 180. Moving now to the bottom left, the angle between a tangent and a radius is always 90 degrees. The alternate segment theorem, which is hard to describe, but basically if we have a tangent and then draw an angle off from it, then we can see the relationship between the angles to the tangent and then the angles within the triangle that's formed. And then on the bottom right we have that from any point you can only draw 2 tangents, and the distance from where those tangents cross to the circle is the same. So we're going to look at the angle in a semicircle, and the theorem is that the angle made by lines drawn from the ends of a diameter to the circumference of a circle is 90 degrees. Proof. So we draw a circle and we have a diameter there, so we have the situation described is drawn there, and what we do is we draw an extra line in from the centre to the point on the circumference. And what that means is that we have 2 angles the same there because AO and OC are of equal length. They're both radii. That means we have an isosceles triangle. That means those 2 angles I've marked as alpha must be the same. Similarly, in the other triangle, OB is a radius, OC is a radius, so that means the angles beta must be the same. Now from there we can then say that the angles in a triangle add up to 180, so we have alpha, then we have alpha plus beta, which is the angle at C, plus beta, the angle at B, they must add up to 180. That means we have 2 alphas plus 2 betas is 180, which means that alpha plus beta must be 90, which is what we set out to prove. Now, for a properly formal proof, you might write a bit more there. You might say AO equals OC, therefore alpha and alpha are the same, but the essentials of the proof are there. And then you make a final statement, therefore ACB is 90 degrees. Then you put a little square. I don't know if you've seen that before, but what that is a symbol that says end of proof. That's saying I have proved what I set out to prove. So that's a mathematician's symbol. Okay, we'll have a look at the angle to the centre and the circumference. Theorem: the angle from an arc to the centre of a circle is twice that of the angle from the arc to the circumference. So again, we'll have a picture of that. So A and B is our arc, and we have the angle BOA and we have the angle BCA. Now, as is common in these proofs, just like the previous one, we're going to put an extra radius in. So we're going to have a radius from O to C. And we can therefore say from the same sort of argument as we had before that the angle at B is alpha and the angle at C is alpha, with the line from BC, that is. Next, we also have that OA and OC are radii. That means if the angle at A, so OAC is beta, that means the angle OCA is also beta, and that means the angle from A to C to B, which I've marked as beta minus alpha, the reason that's beta minus alpha is that those two angles must add up to beta. So beta minus alpha plus alpha is indeed beta. Okay, we're next going to think about that point there, and we're going to use opposite angles, and we're going to call those gamma because they must be the same. And now we've got all the angles on the diagram that we need. Now we want to find out what gamma is because that's going to be helpful to us. Now in the triangle A to the red blob, which I should have given a letter, but never mind, A to the red dot to C, we have beta and we have beta minus alpha, and then what's left over is the gamma, so that means gamma must be 180, take away those two angles. So 180, take away the beta angle that's at A and the beta minus alpha angle that's at C, that gives us gamma. And we can tidy that up a bit because we've got take away minus alpha, so that's plus alpha, and we have minus 2 beta. So gamma is 180 plus alpha minus 2 beta. We also have that the angle at O, the AOB angle, so that's the angle from our arc to the centre, is 180, take away the existing angles there, which are alpha plus gamma. We can replace gamma by the gamma we've just worked out. If we add an alpha, that means we have the gamma, which is 180 plus alpha minus 2 beta, but now we've got an extra alpha, so that's 180 plus 2 alpha minus 2 beta, and that's in the bracket there, and of course we've got 180 minus that. And when we tidy that up, 180 minus 180 is nothing, but we have minus 2 beta, so that's 2 beta, and we have minus plus 2 alpha, so that's minus 2 alpha. So we have 2 beta minus 2 alpha, which means we have 2 beta minus alpha, and that is 2 times the angle at ACB, which is the angle subtended to the circumference from the arc. And we've therefore proven the theorem. So we do our little square. Okay, another one that's very important geometrical fact. The perpendicular from the centre to a chord bisects the chord, and you'll sometimes see this written the other way around. The radius from the centre through a chord that bisects the chord must be perpendicular to it. So they both imply each other, and the proof of this, well, first of all we draw the diagram, and what we know is we have a chord which is AC, and we have a radius, the perpendicular from the centre, and that, as it says it's a perpendicular, that is perpendicular to the chord. What we don't know is whether it bisects it yet, because that's what we need to prove. So we draw again, it's that same thing of drawing radii in, so we draw radii from O to A and from O to C, and they are both radiuses, so we know that OA equals OC. If we mark that point there, the point of intersection between our original lines as X, then we know that AX is the square root of OA squared minus OX squared, and it's also equal to OC squared minus OX squared. So that means A to X is equal to X to C. And that means we've finished, because with AX being equal to XC, that means the line bisects AC. Okay, we're also going to do a beautiful proof. I think they're all beautiful, but this one's, I think, particularly lovely. The radius to the point at which a tangent touches a circle is perpendicular to the tangent. Okay, so we have our diagram. there is a radius from O to B, there is a tangent, and we know intuitively that they're going to be perpendicular, but we do need to prove it. Okay, so we assume that OB is not perpendicular to T. Now this is called a proof by contradiction, and it's actually part of the specification for A2 mathematics, so you won't be doing it just yet within the specification syllabus, but it's a nice thing to have a little preview of, and it fits in nicely here, so go with it and see if you can follow it. So we're assuming the opposite of what we want to prove. Okay, now we're using some symbols here which you may well have seen in some of the previous videos, but if not, I'll explain them. The backward E is there exists, S dot T is such that. So what that line says is there is a point C such that OC is perpendicular to T. So it must be possible to draw a line from O to the tangent that is perpendicular. And there it is. And it looks ridiculous, I know, but it's part of the proof, and it could be just that I've drawn it badly. Maybe there is a line that isn't going to the point B that is perpendicular. In fact, if OB isn't perpendicular to T, then there must be a line somewhere. Now, OBC in this case therefore has to be less than 90, because you can only have one 90-degree angle in a triangle, in the triangle OBC. So that means the angle at B must be less than 90, and that means the angle at B is less than the angle at C, because we know from what we've said that the angle at C is 90, and that means the length OC has to be less than the length OB, because it's opposite a smaller angle. And that doesn't make any sense, because we know that OC is bigger than OB because it's bigger, or longer rather, than a radius. And that means we have what's called a contradiction. And that symbol with the two slashes going both ways looks a bit like a hashtag symbol. That means contradiction. So we started with the assumption that OB was not at right angles to T. Every step we've done is a permissible mathematical step, but we've ended up with a statement we know must be false, i.e. that OC is less than OB. We know that can't be true, and therefore the assumption we started with must be false, because it's led to a falsity. So, since our assumption was that OB is not perpendicular to T, we have actually proven that OB is perpendicular to T. And as I mentioned before, this is a proof by contradiction, and this is covered in more depth in A2.